Hi and welcome to this Leaving Cert Higher Level Maths probability video where we're looking at the binomial distribution, also known as Bernoulli Trials. So the binomial distribution can be used when we want to find the probability of an event happening multiple times and when the order does not matter. So we have a formula for this and it's on page 33 of our log tables and it looks like this. So the probability of x happening or times is n choose or p to the power of or q to the power of n minus or, where or is between 0 and n. So when we're working with the binomial distribution, it's important to understand when it can be used. So it can only be used if there's a finite number of trials. What we mean by this is it's not possible to use it if we want to keep going until a certain event happens. There are only two outcomes, that's why it's called a binomial distribution, two outcomes, and they are success and failure. So success is what we want, failure is what we don't. So although we call this success and failure, we don't necessarily mean that it is good versus bad, it's what we want versus what we don't want. Trials must be independent of each other. So it's important that when one thing happens, it doesn't affect the next thing. So for example, if I were to roll a dice 100 times, it doesn't matter what outcome I get on the first one, that will not affect the second one. The second outcome will not affect the third, and so on. They are independent. The probability of success is the same for each trial, so it does not change. So that's quite strongly linked there to that independence, that it's important that the probability of success, that P in our formula, is going to stay the same. And here is our formula. So n is the number of trials, or is the number of successes, so the thing we want. So it's n choose or. And in your calculator, you'll see this as n c or. So this looks like this in our formula, but they mean exactly the same thing. P is the probability of success, and it must be written as either a fraction or a decimal. And Q is the probability of failure. So Q is always going to be equal to 1 minus P. And that's because there are only two outcomes, either success or failure. Therefore, the two probabilities must add to 1. Let's look at an example. A fair six-sided die is rolled 4 times. Find the probability that a 6 comes up exactly 1 time. One of the main questions I get when we look at this is, the questions are fine, working with them is fine, but how do I know in an exam situation that I'm meant to use the binomial distribution or Bernoulli trials? So let's discuss that before we even work into the formula. The reason we would use the binomial distribution here is we've something happening multiple times. So we're talking about, we roll a die 4 times, we want a 6 once. The problem is we don't care when we get that 6. It could be the first time, it could be the second time, it could be the third time, or it could be the 4th time we roll that die. So it's important for us to take account of all the possible ways that can happen. So think of that back to our choosing. And that's where that binomial here, the binomial distribution is going to come into play, that NCOR, which gives us all the possible ways it can happen. So when we don't know the order, that's how we know we're meant to use Bernoulli. So our probability is going to be equal to n choose or, p to the power of or, q to the power of n minus or. So let's break that down. N are the number of trials, and that is 4 because the die is rolled 4 times. Or is the number of successes. So in this case, the success is getting a 6, and we get a 6 exactly once. So or is 1. P is the probability of success. So what's the probability of getting a 6 on a dice? And that's 1 in 6. And Q then is the probability of not getting a 6, which is going to be 5 out of 6. Or it could be 1 minus P, which is 1 minus a 6th, which is 5 over 6 as well. So 2 different ways to get to that same answer. So our answer is going to be 4 choose 1 times the probability, which is a 6th, to the power of or, which is 1, and then 5 over 6 to the power of n4 minus or, which is 1. So if we wanted to write this into our calculator, we could write that as 4C1, 4 choose 1. This is just a 6th, and then this is 5/6 to the power of 3. Notice how our powers should always add up to the number of trials. So we had a 6 to the power of 1 and 5/6 to the power of 3. Added together, that should give us 4. So we go to our calculator and we type this in. And when we do that, we get 125 over 324. And if you want to go to decimal, 0.3858. So often these won't give us an answer as a fraction. Often we have to go and work it as a decimal. If that's the case, they'll be very clear how to do your rounding. So example 2, a survey shows that 60% of the population is female. 4 Dubliners are picked at random. Find the probability that at least 2 are female. So let's look at that word or that phrase, at least. So that means we could have 2 females, or we could have 3 females. That would be fine as well. Or we could have 4 females. So we have a few different options here. So 2 female or 3 female or 4 female. Now, I can work that through and I could say, well, let's work out the probability of 2 females, 3 females, or 4 females using the adding. So OR is adding. So get the probability of picking 2 females, get the probability of picking 3 females, get the probability of picking 4 females. Or the alternative is, so that's one option. The alternative is we could figure out, find the opposite. So we could have 1 minus the probability of picking not 2 female, the opposite to at least 2, which means no female, or picking 1 female. So either of those ways are going to give us the right answer. We could work 3 probabilities, add them together, or we could work 2 probabilities, add them together, and take that away from 1. So much of a muchness with regards to what way we could work. It's not going to be any quicker, but I'm going to work backwards. I'm going to use the 1 minus. So let's work out the probability of choosing no females. So N, we are choosing 4 Dubliners, or means we're going to have no females. P, the probability of picking a female is 60%, but we're going to work in either decimal or fraction. I'm going to put it as decimal, 0.6. Q is then the opposite to that, to 0.4. So this is N, choose OR, P to the power of OR, Q to the power of N minus OR. So we're going to work that bit out. Then we're going to work the probability of 1. So for this, we're going to have N is again 4, OR is going to change to 1. The probabilities will not change. So we still have P is 0.6 and Q is 0.4. So this is 4, choose 1, 0.6 to the power of 1, 0.4 to the power of 4 minus 1, which is 3. And we're going to work these 2 out, add them together, and take away from 1. So 4 choose 0 is 1, 0.6 power 0 is 1, so we have 0.4 to the power of 4, and that works out as 0.256. 4 choose 1 is 4 times 0.6 times 0.4 to the power of 3, and we get 0.1536. We're going to add these 2 together, and we're going to get the probability of 0 or 1 female is going to be 0.1792, and then we're going to do 1 take away that answer. Excuse me, and we're going to get 0.8208. Since the question gave us percentage, we're going to change this to a percentage, which is 82.08%. Now, let's look at an example where the binomial distribution is required, but it's required in a slightly different way. So a fair 6-sided die is rolled repeatedly until 2 6 appear. Now, I initially said at the start of this video that we couldn't work binomial in that case. However, they have another line here which says, find the probability that it will take exactly 10 rolls. So they are giving us, I suppose, a finite number. And we need to break this up into things we know happen and when, and things we know happen but we don't know when. So in this case, we have 10 rolls. We're going to keep rolling until 2 6s appear, so we can break this question into 2 pieces. We're going to break it into the first 9 rolls. So that's it. And, that word and coming back to us, and meaning multiply, the 10th roll. Now, if we're going to keep rolling until we get 2 6s, what must have happened on that 10th roll is we got the second 6. Now, I actually don't care that it's the second 6. All I care is that I got a 6. So the probability of that happening is 1 in 6. The word and means we're going to have multiplication. Okay, so then if the second 6 happens on the 10th roll, what has happened in the first 9 rolls? Well, we must have had 1 6 at some point. We don't know when, but out of those 9 rolls, one of them had to have been a 6. Now, we don't know when it happens, we don't know the order, therefore it must be that binomial distribution that we use. So we're going to do n, which is 9, C or, so choose or, which is, 1, because we get 1 6. The probability of getting a 6 is 1 in 6 to the power of 1. Probability of not getting a 6, 5 over 6 to the power of 9 minus 1, which gives us our 8. And now we have the 2 parts of this question. We have the Bernoulli or the binomial piece at the start for the first 9 rolls, because we don't know when it happens, and then the 10th roll we know that we get that 6, and we know that happens on the 10th roll. That's not Bernoulli, we know when that happens. So let's put this into our calculator. We have NC1, so that's 9 choose 1, which is going to give us 9 times 1/6 times 5 over 6 to the power of 8, and we multiply that by a 6, and when that goes into our calculator, we're going to have 0.058142, and we can put that back to a percentage, which is 5.8%. So let's look at an exam question where we have to use that binomial distribution or the Bernoulli Trials. So Mary plays game B 6 times. Find the probability that the arrow stops in the €4 sector exactly twice. So we play this game, so Mary plays this game 6 times. And we want to find the probability that it stops in the €4 sector twice, but we don't know when. So if they said it was the first 2 times, we'd know when, and then we wouldn't need the binomial distribution or that Bernoulli Trials. We will be able to say exactly when it happened. But since we don't know, this is how we know we have to use the binomial distribution. So let's break this down. N is how many trials, so we do it 6 times. Or is how many successes, so we get 2 successes. P is the probability of success, which in this case is landing in the €4 sector. So there are 6 sectors. They are equally spaced, which means there is a 1 in 6 chance of getting a 4. And Q is the probability of not landing on a 4, which is everything else, which is 5 over 6. So this is going to be 6 choose 2, 1 over 6 to the power of or, which is 2, 5 over 6 to the power of n take away or, so 6 take away 2, which is 4. So be really careful when you're writing those NCORs that you're not putting a line in and not confusing it for a fraction. So to put it into your calculator, this is 6 choose 2. It looks like that. We get 1 in 6 to the power of 2, 5 over 6 to the power of 4. So 6 choose 2 is actually 15. This works out as a fraction 3,125 all over 15,552. And that works out as approximately 0.2. So our final example is another exam question. We're talking about an experiment that consists of throwing 2 fair standard 6-sided die and noting the sum of the 2 numbers. If the sum is 9 or greater, it's recorded as a win. 8 or less, it's a loss. So I suppose we don't need to actually do the adding, but if we think about where we're going to get a 9 or greater, so I'm going to start in around the middle. I'm going to say, well, 2 plus 6 is only going to give me 8, so there's no winning. So 3 and 6 will give me 9, so there's a winner. 4 and 5 will give me 9. 4 and 6 will give me 10, so that's fine. 5 and 4, 5 and 5 will win. 5 and 6 will win. 6 and 3 will give me a 9. So then anything below this will also be a winner. So this whole section that I've highlighted in yellow, they will all be winners. Everything else will be a loss. So this is what our table looks like when we fill it in. LLL, where there is a loss, and anywhere where we're going to get some that's greater, well, 9 or greater. So we're adding these. We're going to have our win. So the experiment is repeated until 3 wins occur. Find the probability that the third win occurs on the 10th throw of the 2 dice. So here we have that kind of Bernoulli plus, where we're kind of working Bernoulli and a little bit extra. So let's break this down. So we're talking about the third win happens on the 10th throw. So let's break this into 9 throws at the start, and then we have the 10th throw. So that they are the 2 parts of our question. On the 10th throw, we get our third win. So I don't really care that it's the third one here. All I care about is I win. What is the probability of winning? Well, there's 36 outcomes in our table, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the probability of winning is going to be 10 over 36 or 5 over 18, whichever way you want to work it, which means the probability of losing will be the opposite to that, which will be 26 over 36 or 13 over 18. So probability of winning here is 5 over 18. The and is a multiply. Now the 9 throws, what we know happens is we get 2 wins. Now we don't know when those wins happen, so this is going to be the Bernoulli or the binomial distribution piece. So we have 9 choose 2. The probability of winning, which is 5 over 18 to the power of 2, and then the probability of losing, which is 13 over 18 to the power of 7. So that is our Bernoulli piece or binomial piece, whatever way you want to think of it. And the binomial, the binomial is getting the same from the fact there are 2 outcomes, success, failure. Bernoulli, it's kind of more of a slang that is named after a mathematician. So let's work this through and put that into our calculator. So into our calculator we put 9C2. 5 over 18 squared, 13 over 18 to the power of 7, and multiply that by 5 over 18. And we want this correct to 4 decimal places, so we get 0.0791.